Welcome to class number 6. In the present class, we will learn about sensors that are based on nanowires. We will start first with the definition of nanowires, as well as their unique properties that would be of utility for the sensing applications. A nanowire is defined as any solid material in the form of wire with a diameter of 1 to 100 nanometer. An important property of the nanowire is the aspect ratio, namely, the one that means that the length divided by the diameter. Typical nanowires exhibit aspect ratios, or in other words, length to width ratio of 1000 or more, which actually means that the length of the nanowire is 1000 times larger than its diameter. At these scales, quantum mechanical effects are quite important. Many different types of nanowires exist, and these include, among the rest, metallic nanowires, semiconducting nanowires, and insulating nanowires. Molecular nanowires are composed of repeating molecular units, either organic or inorganic, and this consists in an important class of these nanowires as well. New forms of nanowires include also core shell superlattice nanowire. Compared to other low-dimensional systems, nanowires have two quantum-confined directions, while still leaving one unconfined direction for electrical conduction. Basically, this allows the nanowires to be used in applications where electrical conduction, rather than tunneling transport, is required. Because of their unique density of electronic states, it's expected that these nanowires exhibit significantly different optical, electrical, and magnetic properties than their bulk counterparts. Nanowires are promising materials indeed for many novel applications due to their unique electrical, optical, thermal, and mechanical properties. The large surface-to-volume ratio of the nanowire allows one to create extremely sensitive charge or field sensors in chemical and biological systems for the detection of charged particles at molecules at low concentrations. This could be illustrated in the left upper image on the screen. Nanowire also possess interesting optical properties when they are fabricated from group number 3. This semiconductor absorbs and emits light efficiently over a very broad and useful energy range from the UV to the visible IR wavelength. These nanowires are the basis for commercial products such as visible LEDs and blue laser diodes. Recently, one-dimensional nanostructures that are based on nitride semiconductors, including nanowires and nanorods, have attracted attention as a potential nanoscale building blocks for enhanced performance or functionality optoelectronics, sensing, photovoltaics, and electronics, as could be illustrated in the middle image on the screen. In a few instances, nanowires possess thermoelectric power, also called the Seebeck coefficient, namely a measure of the magnitude of the induced thermoelectric voltage in response to a temperature across the material. As a representative example of this property, you might take a look on the hierarchical nanowire structure that is made from indium telluride, as presented in the right side figure of the top panel on the screen. This nanowire exhibits a remarkable enhancement in the Seebeck coefficient of about 43% over that reported of the corresponding thin film at room temperature. In addition to their electrical, optical, and thermal properties, nanowires possess improved mechanical properties. Friction and shear strength at the nanowire substrate interfaces critically influences the electrical, mechanical performance and lifetime of the nanowire-based nanodevices. This could be illustrated in the bottom image on the screen. In the following slides, I will provide a more detailed discussion on each of the properties presented in the current screen. We will first start with the electrical properties of the nanowires. A one-dimensional system such as nanowires has remarkable properties and potential in nanoscale electronic devices. They are often configured in field effect transistor structures. Important factors that determine the transport properties of the nanowires include the wire diameter, which is important for both classical and quantum size effects, material composition, surface conditions, crystal quality, and crystallographic orientation along the wire axis of the material. Electronic transport phenomena in low-dimensional systems can be roughly divided into two main categories. The first category is called the ballistic transport, and the second category is called diffusive transport. Ballistic transport phenomena occurs when the electrons can travel across the nanowire without any scattering. This only happens for short nanowires with length diameter to the mean free path of the carrier or the electrons. For nanowires with length much larger than the carrier mean free path, the electrons, or on the other hand, the holes, undergo numerous scattering events when they travel along the wire. In this case, the transport is in the diffusive regime, and the conduction is dominated by the carrier scattering within the wires. Besides their electrical properties, as mentioned earlier, nanowires have unique optical properties as well. Several advantages and applications that arise from the optical properties on the nanowire include, among the rest, the flow of the optically encoded information with nanoscale accuracy over distances of many microns may be controlled for nanowire structures. This can be applied actually in the future for high-density optical computing. Also, devices that are based on optically sensitive nanowires have a high potential for photovoltaic cells or phototransistors. In this context, please note that phototransistors are a kind of transistors in which the incident light intensity can modulate the charge carrier density in the channel. Organic nanowire phototransistors exhibit interesting photoelectronic properties upon different light irradiation. These nanowires yield much higher photoconductive gains and external quantum efficiencies than their thin film counterparts. In summary of this session, single crystal nanowires are a highly promising alternative to conventional thin film type photodiodes and can be effectively pave the way for optoelectronic device miniaturization. Now we will move to the thermoelectric property of the nanowire. Thermoelectric conversion relies on a difference between hot and cold areas in the device. Heat that is flowing from the hot side to the cold side creates current, which can be captured actually and used to power the device or stored for subsequent use. Bulk material has traditionally been considered a poor material for thermoelectric conversion because its thermal conductivity is too high. This is because heat travels across the nanowire so well that it's difficult to create the necessary temperature differential. In this field, it has been evidenced that nanowires have improved the thermoelectric properties, and examples for this property are given in the present slide. The left image shows that transverse thermoelectric devices exhibit distinct functions as compared to the ordinary thermoelectric devices as described as follows. First, the voltage signal develops perpendicular to the applied temperature gradient. In this case, please refer to schematics number A on the screen. Second, it relates to the compatibility between the N-type and P-type thermoelectric material, which is not necessary since either of them is sufficient for constructing the device. And third, the macroscopic physical properties of the multilayer material can be tuned widely by changing the combination and the periodicity of the constituents. These features provides us new degree of freedom in designing alternative thermoelectric devices. Besides the unique properties of the nanowires for thermoelectric applications, the fabrication of the devices is made more and more cost-effective. Indeed, many efforts have been put on the relatively easy and cost-effectiveness fabrication of such devices. And one example is presented on the right side of the slide. The presented image relates to a stoichiometric and single-phase lead telluride nanowire array that have been prepared using photoresist that is bottomed lithography and patterned with electrode deposition technique. This fabrication approach has been evidenced to provide a control over the wire width and thickness and the suspension of the nanowires across 25 micrometer air gaps. Among all the properties of the nanowires, their mechanical property is one of the most highly structure dependent. The figure in the present slide shows a side view of the type 2 zinc oxide nanowire under the elongation process at different stages. From the figure, one can observe that an increase in the strain leads to a gradual growth in the necking regime of the HX structure. And this, of course, can be shown in figures A and B on the screen. This is because some of the zinc oxide bond is parallel to the broken axis, and the local HX structure becomes a buckled structure at prominent edge of the cross-section of type 2. Here we note that the structure is clearly buckled at the prominent edge of the cross-section of the nanowire, while it's slightly buckled at the central region. In addition, the phase transformation is generated symmetrically along the axis of the nanowire, as seen by the rectangulars in figure A and figure B on the screen. At the third stage, the stress increases significantly with a slight fluctuation, and it's even higher than the yielding stress at the first stage. The slight fluctuation is due to the phase transformation near both ends, and the significant increase in the stress is caused by the new phase, as shown in figure C on the screen. After the strain passes the maximum stress, the zinc oxide bond is broken by yielding stress of 80 gigapascal, as shown in figure number D. With a continuation increase in strain, the necking deformation gradually induces the nanowire to become a 2-atom wide chain in the middle region, as shown in figure E and figure F on the screen. After a strain of 108%, the 2-atom wide chain is fractured, as seen in figure G on the screen. We reach now the end of class number 6, session number 1. Thank you.